Okay, so we're covering a great deal of material, so I do have some summary slides that I do prepare for the summary videos, and I thought it's always good to throw these back up just as a reminder of where we're at, because we're going to cover three sort of involved topics. So we've already covered and finished, as discussed last Thursday. On Wednesday, we finished rigid body's second law. Now we're in rigid body kinetic energy, work energy. And on Thursday, we will start work energy momentum, which will include, I'm sure with great excitement, angular momentum. And so I find this might be just sort of a helpful set of slides. I did already do this for second law, so if you look at the notes for one note, you'll see them there. So if I have a rigid body and I have a small mass element over here, dm, it's going with a velocity v sub I. The center of mass is going v sub g, and it's a distance x bar, y bar from the center. And if it is, I can write vi is equal to vg plus vi relative to g, and I end up doing the same thing as before, which is a translation plus a rotation. And if I do all of the steps, and again, if you don't want to do the steps in this course for cross multiplication, just write them out once. Once you have them written out once, you already know what the form of the equation is going to be. So vgx minus omega y, vgy plus omega x bar, and you put terms in. Now, if it's in an arbitrary point and you don't, you kind of doing everything relative to it, you can say, well, vgx squared minus twice vgx omega y bar squared, plus vgy squared, twice vgy omega x bar, and omega squared x bar squared. And if you add up y squared and x bar squared, you get r squared, so that's okay, omega squared. And here, vgx squared, vgy squared, you just get vg squared. So the only thing that's left is sort of those annoying little bits in the middle, and you integrate them away by just going over the entire mass, because if it's at the center of mass, half of the integral in y bar will be equal to the other half of the integral in y bar, same with x bar. So those two terms will disappear, and hey, mass is constant, that's good, so mvg squared, so that's good. No, that's good. The last term is r squared dm, and you recognize at this point that r squared dm, even if you don't have to derive it, is just I sub g. So you end up with this new sort of term for kinetic energy. And you have to consider the translational and the rotational kinetic energy. And so kinetic energy becomes 1/2 mvg squared plus 1/2 ig omega squared. So altogether, you have just an additional term, checking your units, of course, as you're doing it, mr squared times omega squared will equal mvg squared. Translation. So you can have translation that is either rectilinear or curvilinear, but if it's just translation, it will not have any rotation of the body, in which case the total kinetic energy is just 1/2 mvg squared. So the object goes along those yellow lines there. If it's rotating, and not so well done on my copying, I have 1/2 mvg squared plus 1/2 ig squared, because I do everything with respect to g. And I probably shouldn't use the acceleration either there. But r squared, g squared, omega squared, I end up with this term right here. And you should immediately recognize, again, fixed point rotation or a fixed 0 point for velocity, that is going to be the parallel axis theorem. And if it's the parallel axis theorem, it's 1/2 I naught omega squared. Finally, you have general plane motion. And general plane motion is just going to be a combination of both. There's no real simplification that you can do. It's just going to be 1/2 mvg squared plus 1/2 ig omega squared. A reminder that this is force, velocity, and distance. So if you're looking for a way to prepare yourself for the final exam, which at this point is about 4 weeks and 1 day down the road, you're going to have to recognize what the problems are. So even at this point, most of the problems that we cover on the final exam you can handle. There are 2 sets of problems that remain, the momentum and vibrations, but those momentum we will start this week. Vibrations next Thursday. So it's a very, very fast course. All right, so you have distances that are measured either as distances traveled, as linear distances, or rotations. So theta is a distance. If you have force on a pin or normal force, there is no displacement of those forces in the direction of motion. And both of those sort of disappear. I forgot to add force of friction here. But force of friction isn't going to do anything either. And so you have no motion or no displacement of the force of friction because it's a 0 velocity point. The other thing to get used to, and it's the only new sort of work, and the reason why you will continue to use work in your problems, is that there is work of a couple moment. And a couple moment just refers to, say, for example, if I had 2 forces that are applied here, their distance r over 2 apart, the result is r over 2 plus f r over 2 del theta, and you'll end up with md theta, theta 1 to theta 2. And so you need to recognize the work of a force in terms of how you're looking at things. This has caused a lot of problems on Piazza, and I understand that, but really you have 2 different sorts of ways of looking at all of these problems. You have T plus sum of all of the work, which combines conservative and non-conservative forces. So non-conservative forces at this point, we're going to throw in moments. Because if you have a moment, you can't really reverse the work. Anyways, all right. But for this right here, you have T1 plus V1 plus work 1 to 2, T2 plus V2. All you've done is you've separated out the conservative forces from everything else. And those conservative forces right now are gravity and spring forces. So you have both of those, and we always, I mean, the big difference is that we are defining everything with respect to the center of mass. So for this set of lectures, I won't be posting them till probably Wednesday or Thursday, dependent on how things are. But that really is all you need to know about this particular chapter. Questions? Oh, that was easy. Good. So where we left off last time, I have a 25 kilogram bar rotating downwards at 2 rads per second. Spring has an unstretched length of 0.45 meters and a spring constant of 100 kilonewtons per meter. Excuse me. To what angle measured down from the horizontal does the bar rotate before it stops? Now, what you're looking at, because of the way, and this is going to be a common issue when you're looking at problems with rigid bodies, springs, and cantilevers, is that they're put on a wheel. And the wheel is there only to ensure that the spring stays straight. And it makes the geometry easier. It's there to help you. But, you know, that's all it's there for. That's why we do that particular form of the problem. Where we also go is, and this is where we left off, is I have the initial length, I have the final position, and because of the way this system is rotating, I have done a bad thing, which is to rotate positive as clockwise. Now, often with problems of this nature, especially with the ones in work energy, remember that the results are scalar. And so I'm not going to worry too much about this here because I'm not going to do any type of vector math. All right, so I have two sort of kinetic energies to deal with. The only mass in this system is the rod, and the rod is rotating about 0.0. So T1, where it starts, T1 is equal to 1/2 I naught omega squared. And at this point again, you've done enough of these that moment of inertia of a pin slender rod you know is 1/3 ml squared. So 1/3 ml squared. You have spring potential that you're going to deal with, which is 1/2 K L1 L unstretched squared. T2 is equal to 0, and V2 is equal to something else. And did I put in? Oh, okay. V2 is equal to, or V1 is equal to 0 for everything. It's just going to be, it's going to drop below the datum in order to go in. So V2 is equal to minus mg L of the rod divided by 2 sine theta plus 1/2 K length 1 plus length of the rod sine theta minus length unstretched squared. Yep. Okay. So, all right. So when the rod has moved down in position 2, we know that it's already covered L1, and there is L rod, and we're going to run out of space here, sine of theta. So I'm just adding those two parts up so that I go from the from the initial point, which was the L1, and then when I add it all up, it'll sort of work out. Now the L unstretched is right here. That's the only difference. Everything is good. So datum here is clear. You end up with an equation that goes as 360 sine theta squared 24.75 sine theta minus 66.7, which equals 0. It's a quadratic, and if it's a quadratic, you have two solutions. One of those solutions is going to be minus 27.8 degrees, and the other is 23.4 degrees. Now, the only sensible answer is 23.4 degrees. And so this is, again, one of those cases where you're looking, and all I did between this line over here and this line over here is just add all the terms up. So T1 plus V1 equals T2 plus V2. And T2 is 0, the rest is there, so it comes to rest at 23.4 degrees. Questions? Again, sort of, I've kind of put everything so it's positive down, or a positive rotation in the clockwise direction. Which one do I want to do? Nah, I don't want to do that one. Oh, no, I do want to do this one. I have a whole bunch of them, so I have to decide. But this one's kind of interesting. And it kind of goes to a question, again, you know, I I know one of the values of Piazza for me has been that I can sort of have a sense of what's going on sometimes with material. And one of the things that has been really important is kind of wrapping your head around moments of inertia. Moments of inertia are not, you know, they really are just a replacement for mass in a moment equation. So you have a second law term that looks like a mass, and that's all you got to worry about. Most of the time when you're dealing with it in the course, we're going to give you something that makes it easy to extract. Either it'll be a long slender rod, a disc, or a hoop. And you will have to shift things with respect to some other point, so parallel axis theorem, or we'll give you something like a radius of gyration. So you should be familiar with all of these ideas. You don't have to derive a complex shape one. I can guarantee you that you will never do that in this course. At work you may. But at work you're also going to spend a lot of time doing other things. Okay, why is that here? Okay, what is the sorry, I should tell you what the problem was. Consider a sphere, cylinder, hoop. All of them have the same mass. All of them have the same diameter. But what is the velocity after each one has rolled a distance delta h? So if I just sort of draw on this thing, I know that it's got a v sub g, it has an omega, and it has a point of contact c. So it's contacting the ground. I don't know if I said basically, I know it's not going to slip. It travels, I'm just going to have to make that work. It has traveled down a distance h, so delta h. So it starts at the top, it goes to the bottom, it stays in contact with the ground. This is at an angle theta, and there's a normal force here. There is rolling. I want to go with a different color. Force of friction. And I have weight. And same thing here. So, tuck, 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 tuck. And then 1 and 2. So this thing is rotating in the counterclockwise direction. All right, everything's there. So I can say omega is equal to v over r. So at this point, I didn't say it explicitly, but it's rolling without slip. T2 equals 1/2 mv g squared plus 1/2 I g omega squared. I can say T1 plus work, 1 to 2, equals T2. And I could go a little bit further. T1 plus V1, work, 1 to 2, equals T2 plus V2. So at the very bottom, I can declare that to be a datum and a 0 point. So it starts out with 0 velocity, and so I get mgh. Then afterwards, I get 1/2 m plus I over r squared vg squared. I can write it that way. All I'm doing there is just, I have two mass terms. I could have written it as mr squared omega squared, but I want this in terms of the velocity. So I is the only thing that's kind of there. The mass and the height that they've dropped is the same. So all of these numbers, no matter what the shape is that I'm dealing with, are going to be the same except for I and Vg in the end, by the way. So for Vg squared, I have twice gh all over 1 plus I over r squared. No, mr squared. There we go. So again, I have all of this. The only thing I need to sort of work on, and I need to know, sphere, cylinder, and hoop. Okay, so I have a sphere. Its moment of inertia is 2/5 mr squared. For a cylinder, it's 1/2 mr squared. And finally, I is equal to mr squared for a hoop. So this number is going to get larger and larger as I go from hoop to, I'll get there, I'll get 1/2, 1 plus 3/2, 2/3, and 2/5, 5, or 2/5 plus 7/5 on the bottom. So in all of those cases, I'll get different numbers, and I'll get V sub g equals to 10/7 GH, V sub g equals 2/3 G sub h, or squared, and V sub g equals square root GH. If I had a block, sliding on a ramp that's frictionless, omega is equal to 0, and V equals square root of 2GH. This is a good problem to sort of test yourself on to understand why we're doing moments of inertia and why things change. And so 3 different cases here, and you're just looking to see what's happening and why it's changing in all 3 cases. Questions?
How do we know the friction is going down the ramp?
We know the direction of rolling. It's rolling without slip. So, right here, I very expertly pre-drew this. And when I pre-drew it, I knew that the direction of the rolling is counterclockwise. So in order to oppose that motion, I have to have a friction, and maybe it's better to just draw that, that's opposed in this form. So it's always looking at the rolling. Now, if it were slipping down, say it was slipping down a block slipping down, then the friction force would change directions. I'm sorry? These should, if everything goes well and I don't have a crazy Wednesday night, you should be able to get it all then, but we'll see. Okay. Do I want to do that one? No, I don't want to do that one. Maybe I do want to do this one. No, I don't want to do that one. Sorry, I got to choose problems now, so sometimes it's good to think a little bit before I do them. All right, I'm going to do a similar problem to the first one, a little bit, not that much different. All right, so the difference here is that in the previous problem, I didn't have a compound body. So, same sort of setup, in the sense that this is free to rotate. That wheel at C is free to move left or right and maintains everything at a constant vertical sort of displacement. The disc has a 0.075 meter radius. The rod AB has a length of 0.6 meters, and it's 0.3 meters from the ceiling. The spring has a spring constant of 30 newtons per meter, and you're given a pendulum of a mass AB, which is 1 kilo. The mass of the disc is 3 kilograms, and the spring is stretched by 0.9 meters when released and stretched about D. And rotates about D. Find omega when VB is vertical. All right, so, which means I have the wrong number, maybe. All right, I think this is actually, I will figure out what number I actually meant to have there, but okay. All right, we start there. We have force of the spring, which is pushing up. We have mg. Oh, it's 0.09. Thank you. All right. The spring is stretched by 0.09 meters. Okay, blah, 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 for spring. And it rotates about point D. D is over here, which is coincident with the center of mass of this. So we have position 1 and position 2. So it's released, and what you expect to have happen is that this will rotate downwards and drop. And as it rotates downwards and drop, the spring will stretch, the gravitational potential will increase, and everything will go kind of well. All right, and I'm going to define this as my datum. So VG1 is equal to 0. VS1 is equal to mgh, and that's 1 kilogram, 9.81 meters per second squared, and 0. Oh, no. I want it over here. VG2, mgh, 1 kilo, 9.81 meters per second squared, negative 0.375 meters. So this distance is going to be L over 2 plus R. So as it drops, it's going to drop with respect to the datum by that distance. So I put that down as a negative. VG1 I set to 0. I have the force of the spring. I have everything I need there. VS1 is equal to 1/2 KS1 squared, 1/2 30 newtons per meter, 0.9 meters squared, and VS2 is equal to 1/2 30 newtons per meter, 0.09 plus 0.375 meters squared. So now I have the change in potential due to the spring, and again, it's all bookkeeping. Just draw, if you draw the picture, and if you are not solving, so if I solve this with variables, it might be okay, but there's not really variables that are going to collapse in this particular problem. But if I'm putting numbers down, I also put my units. And it's really important as you're going through your solutions that you're writing down what the units are so that you can go back and check what you have. So V1 equals VS1 plus VG2 G1, which equals 0.1215 joules. V2, Vg2 plus Vs2, which equals minus 0.435 joules. T1 is equal to 0. It starts from rest and then it's let to release. And then T2, I'm just doing it about 0.0. And if I do it about 0.0, I just have, well, only the rod dropped, right? Yeah, so is that right? So it's really important, because I know I have a mass of the disk, it's really important that as you're solving these problems that you add in all of the terms that are associated with the kinetic energy. So unless that wheel, that disk, was 0 mass, it contributes to the final kinetic energy. And so as you're putting this together, this is from the rod, this is from the disk, and however you want to write this, this is the parallel axis theorem. And again, we don't really want you to rederive things, but we do expect you to shift things. And knowing how to shift things with the parallel axis theorem is crucial. Make that look like a rod. There we go. So it's D, right? Oh no, I don't need to do that. So what I've done is I can either write this as the moment of inertia about point D, which is for the rod, which is the center, and the disk. So I can add them up and I get this expression right here. Or I can separate it out and just write it as IABG plus I disk times omega squared plus 1/2 mv squared of AB. But I'm going to leave it like this. So T2 equals 0.0895 omega squared. T1 plus V1 equals T2 plus V2. And omega, after putting all the terms in, is 2.5 rads per second. Now again, this is one of those cases where I'm not worried about direction. I know that the direction, however I define it here, is going to be k. Because rotation in this course only occurs about the z-axis. But in addition, I know that that direction is clockwise because I can see that it's clockwise. So I might define, again, as this in this particular problem and say, hey, that's the positive direction, and be done with it. Any questions there? Go ahead.
Can you explain how the second T2 equation is the same as the first one?
Yeah, these two right here. Yeah. So all I did here was use the parallel axis theorem. So IAB about D, D is right here, the center of the disk, is equal to IABG plus ML over 2 plus R. Is it? Yeah. No, it should not be L. It should be L. Sorry. There. Is that what you were asking? Yeah, okay. My notes get old after a while. So, and then you just substitute the numbers in. The number's correct. I re-solve these so many times I kind of forget where I'm doing the geometry. Let's see if I have. Do I want to do this? I'll do this one. All right, you're asked to find, so you have a two-bar linkage, you have a point of rotation, and this is a little bit, this is again a kind of typical case. You have a fixed point rotation here and a translation over here. And, go ahead.
So just a question about the last part, when we remove the R.
Sorry. Yeah.
Yeah, I was just a bit confused about why we're removing the R.
Oh, no, hey, you're sorry. You know, I keep thinking of 17 different problems at the same time, and I keep messing it up. No, that was correct. I did a good job. Thank you. All right. I hate solving problems in my head. I really do. So I've spent a great deal of time trying not to. But all it is, again, is just parallel axis theorem. All right. Two-bar linkage. All right, so I have a two-bar linkage, and the tricky bit here is that the motion is a little bit odd. And so I know what the velocity of the center of mass here. It's going to be Vg, which is equal to omega L over 2. But I don't know on the second mass over here, it's going to be Vg omega L over 2 plus a translational velocity. And I need to consider that as I'm sort of referencing everything using relative velocities. So I'm just asking at this point for omega AB. Okay, distances are the same. And this looks really nice. V1 equals T2 plus V2. And did I spend it? No, I did not. Okay, the system is released from rest when beta is equal to 60 degrees. And then it sort of rotates and flops down. T1 plus V1 equals T2 plus V2. So we can start with that, and we can start to put some forces down. No. And I have AY, AX, and I should put some names on this, A, B, D. B is over here. MG, MG, and dy. So when I start this problem, I have that as my free body diagram. This is a pinpoint, which means it's going to resist motion in both the x and y directions. However, on D, it will resist motion in the horizontal direction or sorry, in the vertical direction, but not the horizontal direction. Which means the free body diagram there looks different. So before it was one that had, or on the left-hand side you have the two forces, on the right-hand side you only have the one. You also have the two weight forces acting downwards. And let's see, we can do this. And we've defined a datum at the bottom. So typically this is something that happens when you're looking at, so the second condition was that beta is equal to 20 degrees. So here beta equals 60 degrees, and that is position 1. Position 2, beta equals 20 degrees. So again, you have the same sort of things. You have weight, and AY, AX, DY, and the only thing that you really are kind of stuck with is what this height is, and that height from the geometry is 0.1283 meters. So it's gone up, or it started at a high point, it goes down, and as it goes down, it's going to gain kinetic energy and lose potential. So we can go here, T1 plus V1 equals T2 plus V2, V1 equals mgh1, V1 equals twice 6 kilograms Okay, so it's twice because you have two bars. I don't need to calculate each bar, I just know that it's going to, it starts at the same high point and it ends up at the same low point. I also know that despite the difference in motion, this will be a symmetric fall. It's not going to sort of do this. It will fall exactly the same way in both directions. But it's going to spread on the right-hand side. It will not change on the left. All right, this is where I did. So at 20 degrees, okay, I know a couple things. I know at A, I really should draw this out. I know that that's velocity of B. At D, I know that that's velocity of D. So this becomes a problem where I can do a reasonable estimate using parallel axis. And if I do that, so to extend this out, I get an instantaneous center of zero velocity here. I also know that the omega of this object is this. I can calculate all of the angles. 70 degrees. That's 0.75 meters. and this is 0.75 meters. And I know both of those things because one, this is an extension of the parallel of the link AB outward. And I know the velocity d is going vertically upward. So they're going to intersect at the same point. So omega's there, and this distance right here ends up being 0.513 meters. So the length of B with respect to the instantaneous center, 0.75 meters. The length of D with respect to the instantaneous center is 2 times 0.75 times sine of 20, which is equal to 0.513 meters. So velocity of AB is 0.375. It's velocity of B really. 0.375 omega. And velocity of D is 0.513 meters times omega BD, and IAB equals IBD, which equals 1/12 ml squared, which when you put the numbers in, 0.281 kilogram meter squared. Okay, so I got that, I've got that. So T2 is equal to 1/2 mv of B squared plus 1/2 IAB omega A or B squared, which you can calculate, 1/12 mvd squared plus 1/2 IBD omega BD squared. All right. So, in order for this to collapse symmetrically, they got to collapse at the same rate. So omega is going to be the same in both. Velocity of B is all related, so it's 1.52 omega squared. And you end up with T2 plus V2 equals T1 plus V1, and omega equals to 3.9 rads per second. Once you substitute that in, you have everything you need to solve through for the rest of it. Velocity of D is the length of D with respect to IC omega BD, and velocity of D is equal to 2 meters per second. This is a very complex problem. The one thing you have to sort of accept, first of all, is that the omegas are the same, so that they can collapse at the same rate. You also have to accept that there's fixed point rotation at A, and there's translation at point D. And I probably should redo this at some point and eliminate the need for the instantaneous center of zero velocity. But it's kind of interesting to have this one case where I do it every so often. But once you have the triangle, it's not that bad. You know that at this position, this is 20 degrees. So you know the 70 degrees. You know the distances. You know this is parallel, so it's 0.75, 0.75. The only one that you don't have is the final angle. And you can get that from the distances. So everything ends up being sort of in terms of